I would like to present about our lab electroplating, which is different agitation rates. Here is abstract. The weight of the electroplated object changes during the electroplating process. The amount of weight increase depends on factors such as the concentration of the electrolyte solution and the duration of the electroplating process. Experiments show that the weight of the electroplated object increased. The weight change were measured at regular intervals, such as every 13 minutes using a digital weight balance.
So now for introduction, electroplating is a critical process in manufacturing and engineering, involving the deposition of a metal layer onto surface through electrolysis. Central to this process is agitation, which ensure an even distribution of metal ion within the electrolyte solution. This agitation is essential for preventing concentration gradients and promoting consistent movement of ions toward the cathode, where deposition occurs. Our experiments specifically investigate how different agitation rates, controlled by a magnetic stir, influence the quality of copper coating on ion mass immersed in a such solution. The goal is to identify agitation conditions that optimize uniform plating while minimizing turbulence, which can lead to surface imperfections. This research highlights the significant role of agitation in achieving high-quality electroplate product by maintaining consistent ion distribution and provide valuable insight for defining agitation parameters in practical electroplating applications.
For our methodology and our electroplating experiment, to deposit the copper into a steel nail, we used electrolysis in a sodium chloride solution. We prepared the steel nail and the electrolyte solution to ensure optimal conditions for deposition. During the experiment, the nail served as the cathode, while copper wires were anode, facilitated the transfer of copper ions through the solution. We varied the electrolysis durations and agitation rates to investigate their impact on copper deposition. Our measurements included tracking the weight gain of the nail and calculating the resulting thickness of the copper layer.
In this experiment, we investigated the impact of different agitation rates on the weight change over time. This table summarizes the initial and final weights of the nails subjected to low, medium, and high agitation rates over 10 and 30-minute intervals. Observations show that all the samples began with an initial weight of 9.37 grams. After 10 minutes, weights increased slightly across all agitation rates, with the final weights being 9.42 grams for low, 9.5 grams for medium, and 9.6 grams for high agitation. After 30 minutes, further increases were noted, resulting in final weights of 9.45 grams, 9.55 grams, and 9.62 grams for low, medium, and high agitation, respectively. The weight differences after 30 minutes were 0.08 grams for low, 0.18 grams for medium, and 0.25 grams for high agitation, indicating that higher agitation rates affect and causing greater weight increases. This experiment also highlights that how agitation intensity influences the absorption or retention properties of the materials tested.
Now, I will present about the observation. Throughout the experiment, a copper rod served as the anode, positive terminal, and iron nail as the cathode, negative terminal. Upon starting, foam around the iron nail, followed by cloudiness in the electrolyte and eventually muddy water. The iron nail develops a black-green coloration on its surface, indicating potential corrosion products, while the copper rod surface color fade, suggestive of different chemical reaction. Then, what we can observe is the weight measurement of the iron at the cathode show gradual increase post-electrolysis, likely due to deposition from the copper rod. With the increased agitation levels, iron will consistently 10 and 30 minutes, accompanied by a darker black-green hue on the iron nail and continue fading on the copper rod surface color. This observation highly distinct electrochemical behavior and corrosion tendencies of copper and iron under experimental conditions, illustrating the effectiveness of electroplating processes despite varying agitation rates.
Now, I'll present the detailed calculations of our experiment on the increase in thickness due to the copper deposition. The half reaction considered is Cu2 plus 2E minus 2Cu. Then we will calculate the surface area of the submerged nail, and we calculate that the surface area of the nail was 1.3194 cm squared. By using the current density and the area, we can determine the current value to be 0.343 ampere. Then, after 10 minutes, which is 600 seconds, this will produce a charge of 205.8 coulomb. The mass of copper deposited, derived using the Faraday's law of electrolysis, amounted to be 0.0678 gram. This mass corresponds to a volume of 0.0076 cm cubed, given the density of the copper. So consequently, the increase in thickness was calculated to be 57.6 μm for low agitation, 57.98 μm for medium agitation, and 58.13 μm for high agitation. Notably, these values are all greater than the minimum requirement of 50 μm. Hence, this experiment has demonstrated a clear relationship between the agitation rate and the copper deposition thickness. Now I'll present the question. First question, what material should the plating valve consist and why? The plating valve should consist of copper sulfate, sulfuric acid and chloride ions and water. Copper sulfate is crucial as it transfers the copper ions for deposition. The chemical reaction Cu2 plus 2A minus 2Cu where the copper ions are reduced and deposited onto the nail. Sulfuric acid also used to maintain the acidity of the solution, improve the conductivity and prevent the formation of unwanted substance. Chloride ions enhance the quality and smoothness of the deposited copper layer, ensuring a fine finish. For the second question, the ions presented in the electrolyte are Cu2 Cl and Na Cu2 are reduced at the cathode to deposit the copper onto the nail. Chloride ions improve the quality of the deposited copper by preventing the formation of large copper grains, ensuring a smooth and fine layer. Sodium ions help to maintain the strength and conductivity of the electrolyte. For the third question, at the cathode, the copper ions are reduced and deposited as solid copper on the nail. Therefore, the reduction of the copper ions can be expressed in the half reaction Cu2 plus 2E minus 2Cu, while at the anode, the copper metal from the electrode dissolves into the solution as the copper ions. Therefore, the oxidation of the copper metal can be expressed like Cu to Cu2 plus 2E minus. For the fourth question, at low agitation, the electrolyte moves slowly, causing limited copper ion diffusion and slower deposition with hydrogen bubbles forming at the cathode. Medium agitation speeds up the mixing, ensuring even ion distribution and consistent supply to the cathode, resulting in better copper plating. High agitation intensifies the mixing, allowing quick ion diffusion and smooth, uniform copper plating aided by the hydrogen bubbles removing the turbulence. For the fifth question, yes, the final weight differences are observed due to several factors. Higher agitation speed enhance the copper ion flow and deposition, increasing the weight as well, while lower speed will result in slower and less uniform deposition. Better surface preparation also leads to efficient plating and more weight gain, whereas rough surfaces cause poor plating and less weight gain. Additionally, higher copper ion concentration in the electrolyte results in greater weight gain due to more available copper ions for deposition.
The experiment demonstrated effective copper deposition on steel nail via electrolysis. Longer durations and higher agitation rates directly increase copper deposition, as evidenced by the measurable weight gain of the nail and the calculated thickness exceeding the required minimum. Our study highlighted the crucial impact of controlling parameters like current density, electrolyte composition, and agitation rates on the uniformity and quality of copper deposition. Moving forward, these insights will advance our knowledge and application of electrochemical deposition techniques in material science and engineering, paving the way for more precise and consistent results in future experiment and industrial applications.